Today's our first stats class, and there you've learned a lot of Python, right? You've learned kind of everything you need to know about Python to be dangerous. Um, you haven't learned everything there is to know about Python necessarily, but you have kind of the amalgam of tools that it takes to have a complete language, and we can think about that. What you've learned so far, you could take those constructs into another programming language, actually, and those constructs will hold, right? So, the basic algorithmic understandings that you have thus far, those translate across languages. If you were to go learn R or Java or some other language, you'd be able to take what you have so far, and there would be some analog across them. So that's pretty cool. Python goes really deep. There's things that are more Pythonic, less Pythonic. And I want to qualify the way that I lecture in this course as being somewhat less Pythonic. And I do that for a reason, or a set of reasons. The main reason is we are primarily interested in you being able to take an idea, a statistical concept, or some procedure that you conceptualize in your head, and turn that into code. We don't need you to do that perfectly in a Pythonic way, in the way that somebody who's been writing Python for the last 8 years or who has done some extreme intensive study of the language would do that. We don't need you to do that. Our goal here is to have you be able to take something and express it. And if you can express a statistical concept or a set of statistical concepts or probabilistic concepts in code, that's great. And you can take, fairly complex algorithms and write something that works. So there are going to be a lot of moments where I write something that, if you have a computer science background, you might be slightly appalled, and you might say, well, there's this much better way to do that. And yeah, there are a lot of better ways to do things. I'm going to write code that is more accessible for a wider variety of people, and it's going to be code that you can look at it and understand the procedure inherently. So I don't know to what degree Clark has talked about this. There is code you can write an extremely dense one-line statement that in Python that does, like 10 things. I'm probably not going to do that very often. Every once in a while, maybe I'll say, hey, here's this other way that we can do this that, ends up looking like this unreadable blob. Maybe when you get to a point where you are writing unreadable blobs for production, that's awesome, as long as the rest of your team can read those things as well. So I just want to put that qualifier out there before we move forward. This is all about translating statistical concepts, probabilistic concepts, algorithmic concepts into code. So what we're covering today is, some very basic statistics. We're going to ramp into this kind of slowly. We're going to have 2 days for basic statistics, the kind of stuff you would learn in the first 2-3 chapters of a stats book. Mean, median, mode, interquartile range, variance, standard deviation. Some concepts related to sampling, discrete versus continuous data, and maybe just like some reasoning. Why do we associate statistics so strongly with data science? Why do we associate probability so strongly with data science? So with that, let's start with thinking about why probability and stats are so important. And I'm trying this new thing out, just so you know, where I'm screen capturing the slide and I'm bringing it up if it's something that's applicable. So, don't be surprised if there's stuff that swoops up into the screen. Okay, so it turns out that data science as a profession used to be called statistics, and then it got way cooler. And that's maybe not fair to a lot of people. Data science is kind of this abstraction of the sciences, right? There's a lot of experimental design. And you might learn that in biostats. You might learn that in chemistry, right? You might learn that in any number of fields. Data science tends to be an abstraction of the sciences in that way. You spend a lot of time thinking about what research means. You spend a lot of time thinking about what sampling means and qualifying the experiments that you're performing. Now, we tend to do that a lot with code, right? We do it with in procedural ways with data sets. We do it in machine learning ways. So it's not just statistics feeding into this. It's also computer science. It's the advent of machine learning, which arguably does have its roots as much in stats as it does in computer science. But pretty much everything we do has some view from stats, from probability. And that's going to be important, right? You're going to get a data set and you're going to, first look at it and ask, well, what is the mean of this column of data? What would I expect to see in this column of data given the mean and the standard deviation? What is the modal value and why is that the modal value? And you'll use those concepts not only to describe the data, but you'll use those concepts to kind of qualify the data. You might say, well, it kind of seems like there's something wrong here because I have this one modal value. I have this one value that appears so much. And what is that related to? Is that, some default setting of a sensor that, you can use the basic statistical concepts to qualify your data. So that from the time you get your data to the time you validate the machine learning model that you use with that data, you are applying statistics, right? Everything from end to end. A lot of our models are probabilistic, well, let's just say all of our models are probabilistic, so it's important to have, it's important to build your foundation in probability and stats and to kind of gain an intuition around it. Does that mean you need to be out in the theoretical, world of, the cutting edge of theory around stats and probability? No, you don't need to be out there. You need to know what you need to know, and you need to be able to apply what you know. And some of that we're going to do through the course of this, through my stats lectures, and some of that you're going to do in the pre-course before the DSI. And there's a significant chunk of stuff that you're going to do in the DSI. For example, we're not going to do hypothesis testing or confidence intervals. Part of that is because the way that is presented in the DSI is in a more data science-y way and not in a sort of traditional statistics way. And you're going to kind of learn, multiple approaches to that. So there are some things we'll leave out as we go forward. And we are going to focus on applying, procedural approaches to statistical concepts. So there might be times where I describe some kind of process, right? Some phenomenon, and we model that phenomenon with some procedural code. And then we get this big wall of, output, and then we filter that output and get something out of it. And we say, well, the probability of this outcome is, these outcomes from this massive wall of outcomes. And that's not going to be as mathy in a way, right? It's going to be letting the code do something with a, brute force procedure and then filtering that procedure down. There are more efficient ways to do a lot of that kind of stuff, and we aren't going to focus as much on that. So I guess that's another qualifier as we go forward. So that's my justification for probability and statistics. It's very important to us that you get to a proficient level of coding and be able to express some fairly simple concepts with coding. And that's our main focus throughout the course. Okay. So how do we think about, how do we want to think about statistics and machine learning and artificial intelligence? Where do we draw the lines with these things? There's a comic in the notes, and let me just pull this up really fast. I think this this says a lot. Okay, so the comical part is there's a crack on the wall, and he's framing it, and he's describing it as if it's some sort of decision boundary or curve that's being modeled. And depending on who he's talking with, right? When you're fundraising, it's artificial intelligence. When you're hiring, it's machine learning. When you're implementing, it's the specific model, like logistic regression. And part of what you're going to find as you go further into this space is that you're going to be learning esoteric things that a lot of people don't understand. And you're going to try to explain those things, and they're going to say, oh, you mean like machine uprising that's going to, destroy all of humanity? It's like, no, not actually. I don't mean that at all. And they're like, yeah, do you mean like Kurzweil and like we're all going to live forever and stuff? And it's like, oh gosh, like you're going to get this kind of stuff from time to time from people who operate businesses who you're working for. And that's not great. And you're also, the joke that I always make, people will say, here are all my grocery receipts from last month. Can you, predict how my stock portfolio is going to do? It's like, no, these things that people have sort of fundamental disconnects. You are not going to be disconnected in that way so much. And that might end up being a bit of a frustration. How people communicate around this stuff is also going to be a frustration, and then you are going to tailor your communication around it as well, in order to not only avoid frustration but be pragmatic with who you're talking with. I think that just comes with the space, and you'll probably discover that sooner or later if you haven't already kind of discovered that as you've been studying. So the things that we're going to cover with basic summary statistics, measures of central tendency, which is what we're going to do today, mean, median, and mode, and then measures of variance or spread. And I didn't include it in here, but we're also going to think about the interquartile range. We're going to think about outlier detection, and some other related concepts. We're going to just kind of use these concepts because they are fairly simple. We're going to use them as platforms to code functions. And we'll have a number of breakouts for each of these, although we are starting just with measures of central tendency. Like I said, we'll get this started sort of slowly. In our next class, we'll cover variance measurements. So the first maybe obvious thing that we're going to talk about is the mean. And there's just some information on this slide, and then I'll talk about it a little bit more. So the mean is very, very simple, right? We just add up numeric elements and divide by the number of elements. Now, there are a couple things that we've got in here that, I'll just jump over to here. For some of you, maybe you haven't done that much math, okay? And the symbols are a bit intimidating. So I'm going to just walk through the symbols that are on that slide, how we are representing mean. So, this is the Greek letter mu, and this is we use this to represent the population mean. And I'll talk about population versus sample in just a little bit. This is x bar, that's how we describe it, and we use this to talk about the sample mean. Okay, so population versus sample. This kind of necessitates a description here. If you think about everyone in the world and their heights, I think this is an easy one to think about. So here is a pool of information representing the heights of everyone in the world. And within this, let's say we want to describe the average height of all people, which is the mean, right? Or how we're going to think about the mean. If we have recorded all heights in the world, then we can discover the population mean, right? If we know everything, then we know the population parameter, as we call this, which we call mu, okay? Now, obviously, that's not very practical and or possible in almost any case. We are almost always talking about a sample because we're always drawing a sample from a population. So if you think about this, maybe we can get a significant sample of the population, and maybe we get this sample in such a way where, we get a little bit from here and here and here and here and here and here and here, so that sample can be representative of the population. And then our assumption is that when we calculate the average, we are approaching, when we calculate x bar, the sample mean, we are approaching mu, the population mean. We are trying to approximate the population mean. There's some maybe things that are a little obvious in there, like, well, how do we approach mu from x bar? Well, you take more samples, right? Or you take more representative samples. That's one way that you might do that. That's a good way to do that. There are some other more conceptual things that we'll talk about in this regard. But in general, you want to consider a problem and decide if you are dealing with a population and a sample, right? So if I say, okay, you've measured all the heights of a classroom of students, right? Of high school students. What is the mean height of that classroom? So that would actually be a population because you're only dealing in regards to that classroom's parameter, right? The parameter that represents the actual average of their heights. Meanwhile, if you're like, okay, well, you've got this school and you sample, you create a representative sample of all the heights of everyone in that school. What is the average height? Well, that's obviously the sample statistic. So that's, when we're talking about a population, the measurement that we refer to, the way we refer to the measurement is as a parameter. The way that we refer to the measurement of a sample is as a statistic. So that might already imply how often we're, in statistics, how often we're thinking about sampling, pretty much all the time. It's rare that we are specifically talking about a population parameter, although we are generally trying to approach either a theoretical measurement or a population parameter. Okay, so in that sense, how do we think about just the mean in terms of the symbols that we use to represent it? In that slide, there's something that looks like this. 1 over n, this giant E-looking thing, which is, we call that sigma. And sigma, for us, just means summation. Okay, so we're adding everything up. So we go from the first of something, I equals 1, to the nth of something, which is the last element, as we're going to think about it, of A sub I. Okay, so we can use this formula for either mu, for the population mean, or we can use it for x bar. So, we're generally going to be thinking about this as the x bar of A. Well, what is A? A is a list of data points. So, if we've got 5, 9, 3, 7, and 2. 5 is going to be A sub 1, okay? 9 is A sub 2. A sub 3 is 3. Something to notice here is that in the mathematical representation of this, we're using 1-based indexing. And in Python, we use 0-based indexing. So that's going to come up from time to time where, you're like, okay, well, I equals 1, but when you write code for this, you're actually looking at I equals 0 up to n minus 1. It in some mathematical representations, they'll start at I equals 0, or I get 0. But in general, it'll look something like this. You'll start at I equals 1, and that just means the first element of, in this case, A. Okay, so if we were to figure this out, well, that's easy. 14, 17, 24, 29, 26. Great. 26 over 5, right? So this is, 5 points, what is that, 02? Am I being silly? Wait, so 5, sorry. Yeah, 5.02. So our average here is 5.02. And, one nice way to think about this is we'll put these in order. Order A, so 2, 3, 5, 7, 9. And 5.2 or 5.02 sits somewhere like right here, right? It looks fairly central. And that's going to become important in a little bit. How central does X bar look? Because sometimes the mean isn't great at describing centrality in our data. So I think we're going to jump over to some code. I think I have a breakout for you. Oh, you know what? Let me talk about this really quick because it's an extra challenge on the function I'm going to have you write. So there's this concept of the trimmed mean, all right? Trimmed mean, it's a more classical stats concept. Basically, the trimmed mean is just, take off the minimum and maximum n values, okay? So if we're going to think about this in terms of this data set, well, I put A into order, right? I ordered it 2 to 9. If I were to trim this by 1, then I could get rid of 2 and get rid of 9. And that gives us 8, 15. 15 divided by 3 is 5. So the trimmed mean here would actually be 5. Now, we might decide, okay, well, maybe that's a better measure of centrality. Maybe it's not. And that sounds pretty arbitrary, right? Like, suddenly statistics doesn't sound like like very rigorous math if we think about it that way. But if you think about this in terms of sampling, well, a sampling is supposed to be representative, or a sampling process is supposed to create a representative data set, numerical data set, let's say. And what happens if, there's always the probability that you get some really, really huge number or some really, tiny number that isn't common, right? So, in randomness is sort of lumpy. It doesn't mean that you're going to get this thing perfectly. And if you get some massive number, that is actually going to make your mean travel up. It's going to be a higher value. And so, in this case, I wouldn't say that 2 or 9 is not representative. I don't know. I don't know what this is sampling from. But if we had, 2, 3, 5, 7, 9, 9,000, right? We might get rid of 9,000 and 2 to get a better sense of the centrality. So trimmed mean is something that you can apply. We'll show a different rigor, different, arguably better way to do that. To pull your mean back into being reasonable when you have outliers, right? Like 9,000 we could call that an outlier. Trimmed mean isn't the only way to do that, but it is something that you should know. And it's something that we can use as an opportunity to complexify the function that you're going to write. So I have a quick breakout here. We'll do 4 minutes on this breakout. And you're going to code a function, the mean function, okay? The mean function is going to have one parameter. It's going to be a list. LST is fine, whatever you want to name it. And as a bonus, you could put a second parameter that is trim, right? And trim is going to take some numeric value. It could be, maybe you want to trim the bottom and top 1 values, right? So like in the case I just showed you, trimming 2 and 9. Maybe you want to trim, maybe you have a larger data set and you want to trim the first 5 and the last 5. So it'll be a symmetrical trim, if you want to think about it that way. Only implement that if you feel comfortable with the mean function, with writing the mean function as it is. And I will paste in this list of data points so that you have something to test with. So I'll put 4 minutes on the timer in just a second. And the way that I do this, I have a timer. Yeah, I should let you know this. I have a timer in my bash script, and I'm going to do timer 4, and it's going to say 4 minutes remaining. I'm going to stop that for the moment. And when it gets down to the 1 minute mark, it's going to say, it'll post a little message that says, post your answers now, something like that. 1 minute remaining, post your answers now. Just so you know, I prefer that you post your answers in the final minute, unless I explicitly say, hey, when you get to an answer, just post it. And I do say that with some things sometimes. Okay, so that's the challenge. You're going to code the mean function, include a trim parameter if you feel like this is a fairly easy challenge, and you've got the data to work with. So I'll go ahead and start the timer, and go ahead and get started. Okay, so I'm gonna start coding this. A lot of the time, you know, if a challenge is harder or something like that, I might, come off mute and say, hey, do y'all want a couple more minutes on this? With this one, I'll code it and then I'll paste the solution into the channel. There are a lot of good solutions that I'm seeing in there, and that's awesome. So I'll just go ahead and code this. So the name here, simple, right? Mean, and we're going to pass in a list. So I'll code this in the simplest way. We can just return the sum of the list over the length of the list. Okay. And let's see, is that still on my clipboard? Yeah. Okay. So I'll print the mean of A, and let's see what that gets us. 238.3 is what I'm getting from A. So this kind of brings up, is that representative? Is 238.3 representative of the data in A? Not so much, right? Not so much. Seems probably obvious why. It's that 2000 dragging things to the right, dragging the mean to the right. So, in fact, 238.3 is, the second largest value. So I'm going to rework this a little bit to have that trim. What did I name that? Trim parameter. Yeah. So do trim, and by default we'll trim by 0. That trimming by 0 will not remove anything, right? If we trim by 1, we'll remove the bottom and top value. We trim by 2, the bottom 2, the top 2. So the first thing I'm going to do here, I'm going to make a copy of this list. I'm going to do list underscore. That's going to get list.copy. And then I'm going to say if trim. Okay. Oh, you know what? I need to change these down here too. So no matter what, we're still returning. Well, I could leave this as list if. Sorry, I'm over explaining here. So if trim, and I can say if trim, or I can say if trim greater than 0. Those are actually equivalent statements because for us, 0 is Boolean false. Okay, it would be more Pythonic to say if trim, but I'm going to do if trim is greater than 0. In that case, I'm going to overwrite list, and the way I'm going to do that is I'm going to sort it first. I'm going to get the sorted version of the list, and then I'm going to slice it. And this is kind of nice. This is really friendly syntax in Python. I'm going to start at, let's say start at 1 and go to 1 from the back, right? So that's going to drop symmetrically the lowest one and the highest one. If trim is 3, it's going to drop the lowest 3 and the highest 3. So either way, that's going to work. And if I run this again, this time I'm going to trim. I'm going to trim by 1. So trim gets 1. Let's see what that gets us. Oh yeah, okay. So when we trim that by 1, we get 47.75. And that does look quite a bit more central. But I would even maybe, if we're thinking that we shouldn't expect this much kind of deviation out to the right, then I might make a judgment call here and trim by 2, right? And trimming by 2 is going to get us something, 26. And 26 kind of looks like it's right there in the middle. Does that mean that we should go with 26? No, not necessarily, right? This is where you have to apply, more critical thought to it. We could say, well, I don't like the way this mean looks on this sample, therefore I'm going to trim it a whole bunch. But that doesn't mean that you are well representing the data necessarily, right? These really large values, even that 2000, could be a representative value. And if you get rid of it, then you're not going to have a mean that is approaching the population parameter or the assumed population parameter. So that's all about using your best judgment after analysis of the data itself. Okay, so I'm gonna put this in the Slack. I believe there is a question that's going to ask about the trimmed mean in a little bit, and I'll go ahead and comment these out. Oh, and also Clark probably mentioned this, but I am live syncing this, on a timer to GitHub. So this code, this file, should show up on GitHub, within a minute of me posting it here. So, but I'll do my best to remember to also put it in the Slack. Okay. All right, so yeah, I think this is good. Actually, you will need the trimmed mean for this, and there's a little bit of a critical application here. So I'm going to pull this up, and I'm going to set a 4-minute timer. But first, I'll read through it just to make sure it's clear what's being asked for. An article published in the journal Indoor Air considers 2 different air samples to test for endotoxin concentrations. The first in urban households, the second in farmhouses. Here's the urban data set. This list of numbers, and I'll put those in the Slack. And here's the farmhouse data set. Notice these are samples, right? So you might want to think about that. Determine the sample mean for each group. Determine the trimmed mean for each group by trimming the smallest and largest value. So I will paste in that data, and hopefully those commas are usable commas. Let me know if they're not, and I'll fix them really quick. But usable in the sense of being UTF-8 compliant. Every once in a while we run into that issue. So I'll set a timer to 4 minutes, and yeah, go ahead, see where you get with this. All right, so I'm going to start walking through the solution for this. Because I think with these types of problems, people initially get hung up on kind of the workflow of them. It's like, well, how do I take that, get into my code editor, get to an answer, and everything. So I'll show you how I might do that, and we'll go from there. Okay, so I'm gonna copy from the slides. I'm just gonna copy this big block of text and wrap this in quotes. And out of this, I'm going to, maybe I'll do this. So we're going to use urban, and this is going to be a list, right? And this is going to be farmhouse, and that's also going to be a list. So I've got, oh, let's try that again. Okay, that is the wrong character. There we go. Okay, and the first thing we're going to do is determine the sample mean for each group. Well, that's easy enough. I can just do mean of urban, right? And mean of farmhouse. I'm going to tend to, well, at times I'm going to tend to make nicer messages than this, in part because I want to get you used to using F strings. So I'm going to actually just wrap this in an F string, and I'll do something like this. I'll say mean urban, and then, you know what, copy that, all that business right there, and I'll change this to mean farmhouse. And that should be the first, that should be part A. So just determining the mean of those two. I'll go ahead and see what that is. That is a syntax error for some reason. Oh, I see it. All right, let's try that again. Okay, so it looks like mean urban is 21.545454 forever. Mean farmhouse is 8.56, a lot of zeros and a 2. Well, if you think about it, well, there's two different things happening here, right? With these results. And I'm going to just make a case for using the round function. How many of these values are significant? How many of them are meaningful for us? Now we could be rigorous from an engineering standpoint, but I'm just gonna eyeball this, and I'm gonna say, well, I'm gonna round this to, well, let's look at the data. I'm just gonna round this to 1 decimal place. How about that? And I think that's gonna be good enough for what we're doing. So I'm gonna round the mean of both of those. I think you could even make an argument, well, I think rounding to 1 place captures significant digits here well. And all I did was I took round, put that around the call to mean of urban, and, oh, I was going to do 1 place, wasn't I? There we go. And then comma 1 for how many places I'm going to retain to the right of the decimal point. So 21.5 and 8.6, that seems reasonable. So that's part A. Part B is just, it's really the same thing, but I'm filling in the trim parameter. So determine the trimmed mean for each group by trimming the smallest and largest. So why don't I do trim gets 1 for each of these. And we can kind of compare, you know what? I'll leave this uncommented because I think we'll likely want to compare these and ask the question, if it seems that like there's a big deviation between the trimmed version and the untrimmed version. So mean trimmed, trimmed mean. How about I do that? And this is also nice for output because you get meaningful messages. So why don't we look at those results? Okay, 20.5, 21.5 and 8.6, 17 and 8.2. Okay, well, it kind of seems like the farmhouse values, there isn't much difference between the farmhouse mean and the trimmed mean. And I think that, might give us some, a little bit more faith in a way about the samples that we've taken for farmhouse. Now, thinking about urban, there's a bit more travel there, right? Like we've changed by almost 4 parts per million, or I'm not really sure, what that level measurement is, but whatever it is, there is a greater change, the delta between mean and trimmed mean. And if we were to see that, we might even we might not say, okay, well, let's use the trimmed mean. What we might say is why, right? We might say, okay, let's go back and look at the data. One of the questions that we want to answer is this sample representative or effectively representative? Is this high value, and I think there is a fairly high value in here of 80, is that an outlier, or should we consider it to be an outlier? Or, given other times that we've sampled using this method, have we, had this occurrence of, of values that high, right? So there isn't a hard and fast rule here. It takes the critical thought that you turn back toward it to make a decision about whether or not you drop a data point. So I'll go ahead and comment those out. So probably something you notice here is that having outliers or having a large value or a very small value would have a similar type of effect, will take the mean and skew it in one direction or the other. And when we think about that, we say, well, the mean is not resistant to outliers, right? Outliers will pull it in a direction or another direction. So there's another measurement we might use, another metric that we might consider, that is the median. And the median, feels simpler and has a more complex algorithm. So it's simply the middle value of a numeric data set. So there are a couple symbols here, right? I like this one, median, just MED of A. I never use X tilde to represent median, just saying. I never do. But, maybe you'll see it, and maybe it'll be common, someplace where you're doing work. I'm not trying to hate on the X tilde, but I'll generally say MED for median. Okay, so how do we think about median? From an algorithmic standpoint, well, if we're going to think about this in an algorithmic way, let's first make a data set. So A is going to be, how about we do 9, 3, 21, 14, 6, 2, 2, and 7. How about that? Okay. So the first thing that we need to do here is put this in order. Let's see how many plate. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Well, we'll start there. So notice, I'm just going to point this out. This is an even length list. Okay. We've got an even number of data points. Looks like the lowest value is 2. Then there's another 2. So I'll do those. 3. And then looks like 6. And 7. And 9. 14, and 21. So the first thing I've done is I put it in order. And then the next thing I can do is find the central value. All right, so, I'll just do this. I'll just cross these out as I go. And where I'll end up is, there's two central values, right? So in the case of an even list, we're actually going to take the mean of the two central values. In this case, we're just going to add 6 and 7 and divide by 2, which is going to give us a median of 6.5. Okay? So our median here is going to be 6.5. Something to notice, I'm just going to point this out. 6.5 is not actually a number in this data set. So, when we're thinking about the lower half of the data, it would include 6 here, wouldn't it? And the upper half is going to include 7. That's just something I'm pointing out. It'll come back around. Okay, so what if we have an even length list? And I'll just do a shorter list just to point this out. So let's do 1, 5, 3, 974, and 7. Okay. So in the ordering of this, we're going to go 1, 3, 5, 7, 974. And we can use that same process to get to the middle, right? So, and I'm doing that just so I don't make mistakes. And we can see that the median is 5. We just select that as the median. If we were going to consider the top and bottom halves of this, well, what we might do is say that's the top and that's the bottom and this is the median. And maybe not include it. Maybe not include it in either the top or bottom. Something that you might see here is, okay, well, did this massive value 974 even matter? Did it affect the median in any way? We kind of just discarded it, right? And so what we say about this, what we say about median, it's resistant, right? It's resistant to outliers. Okay. So with that in mind, I'm going to put what I'll just call this the algorithm for median. I'll just put it up here. You sort the list, you find the middle value. If the list is odd, just select the middle value, right? And if the list is even, you take the mean of the two middle values. So this is a little more complex than the mean function, but it's not so hard, right? You just need a little condition in there. So I'm going to put a couple lists in here, an odd list and an even list. And then, I'll give you 6 minutes on coding the median function. And then we'll take a break after that. All right, feel free to get started. If you feel like you need 2 more minutes on this, just give me a quick thumbs up in the thread, and I can add 2 minutes. Okay, I'll go ahead and put 2 more minutes on this. Okay, so I'm gonna start coding this. If you feel like you're close, continue working on it. Either way, I'm gonna paste the results of this into the Slack, and you'll have this function to use. And don't feel bad if you didn't get there or if you don't get there in this time. It's more important to kind of figure out why it works at this stage, right? If you can't write it yet, but then you see it, written, and then you go back and study it and pick it apart, that's going to inform how you think about designing algorithms or designing solutions as you go forward. So go ahead and start talking us through this. Okay, so we're coding the median function, and we're going to assume that this is going to take a list. And actually, did I paste in a couple test lists? Is that what I did? Yeah, I did. Okay, good. All right. So ultimately, and you probably see Clark do this quite a bit. Ultimately, we're going to have to call these, right? So, I'll print the median of the odd list and the median of the even list. And I'm also going to print the odd list and the even list, even though we've got them right there. I think it can be helpful to look at the median in context. And maybe I'll just put a space in between. Okay, so when we get to it, I'm going to run that, and we're going to get to see some output. All right, so the first step of this is sorting the list, right? And I'm going to go ahead and sort it. I'm going to make list sorted, and it's going to just be the sorted version of list. And now that I say that, when I print these lists down here, if I actually want to see the median in context, I probably want to sort those as well. So go ahead and do that. All right. So we've got this list sorted. And the first thing that we're going to try to satisfy is if it's odd, right? Because that's kind of the easier. Well, is it the easier of the two? I don't know. But we can think about that. We can take the middle value. So if the length of the list mod 2 is 1, right? If there's 1 remaining after we mod by 2. Now, I'll point this out again. I pointed this out before. 1 is truthy, right? Or anything that's not 0 is truthy in the integers. So I could actually do this. I could say if the length of the list mod 2, the result of this operation is 1, and then 1 would be evaluated as true. But that's just so when you see that it's not confusing. All right, so I'm gonna get the middle index, the middle index value. Okay, not the value itself, but the index itself, and that's easy enough to get. We can take the length of the list and divide by 2. Notice that this uses division, right? So if I want this to be something I can use to index with, then I need to cast it to an integer, right? We can't index by fractions. We can't index by decimal values. And then I can return the sorted version of list sub mid, okay? So that's in the odd case. Let's think about the even case. So I'll just put an else here. That's easy. It turns out in the even case, this statement right here is going to be the upper middle value. And for that reason, I'm just going to take this. I'm going to call it upper mid. Okay, so I've got the upper mid. Well, what's the lower mid? Well, that's easy. The lower mid is going to be this minus 1. This is a situation where maybe we would want to type check or something like that. We'd want to be dealing with a list that's longer than 2 items, right? What's the median of 2 items? Well, it's actually just the mean of those 2 items. So with this, we can return the mean of these 2 indices, right? So we've got list sorted. I'm just going to snag that and don't know why that didn't paste. Oh, there we go. So this is the upper mid, and I'm gonna grab that again and have the lower mid. And maybe that's weird. Maybe I should actually put these in the other order. Doesn't really matter, but just for understanding it. And I'm going to take these and I'm going to put these into a list. And then pass it into the mean function. I mean, I obviously could just sum them and divide them by 2, but this is easy as well. So I can just return the mean of the that lower middle value and the upper middle value. And hopefully that will work. So let's see. Okay. So I'm getting 14 and 12.5. We can try to qualify this, right? 13, 21, 18, 13, 16, 14, 14. Well, that's clearly 14, right? The median there of the odd length list is 14. Now, this even length list, we can get rid of 8 and 16, 15 and 8, 10 and 14, and then we have 12 and 13. The mean of 12 and 13, or the way we're going to think about that, is 12.5. So, don't be hard on yourself if you didn't get this. It is a somewhat more complex algorithm, and I do recommend. There are a lot of things that look like this that you'll have to solve in the future. If you didn't understand what's going on here, go back to it and kind of work with it and see if you can get to a good place of understanding. All right, let's take 6 minutes, just a quick, just 6-minute break, and I will see you all back here shortly. Okay, so I already kind of mentioned this, but I'll just say it again. The mean is not resistant to outliers, right? We can pull the mean in one direction or the other by just having much larger or much smaller numeric samples. The median obviously is resistant to outliers, right? We could have 1, 9, 7, 3, 4, 2, 1 million something. And that 1 million something is going to be irrelevant to the median. So, when we choose between mean and median as, let's say representations of the centrality in the data, it's going to be relative to the data itself, right? It's not going to be exactly one is better than the other in general. It's really about the data. And what we're going to see is that a lot of things really are about the data. So I've got a quick breakout here where you're going to use both mean and median. And if you have time, format your data nicely, your print messages nicely, and if not, that's okay. It's more important just to play around with this and try to get it to work. I will put the this list of numbers in the Slack really quick. And the problem we're thinking about here is these are home sale amounts from Alameda, California for a particular month, and I guess April. Find the mean value of the homes in April, find the median value of the homes in April, and describe why you think mean or median is a better measure of the center of this data, the central tendency of what we think is in the population, and why. So I'm going to put 4 minutes on the clock. And yeah, go ahead and do that. Okay, so let's go ahead and work through this. I'm going to just shrink this down over here. And I'll call this house prices. And I think, yep, okay, good. Now, the first thing that we're going to find is the mean value of the homes. So the simple print statement, I'll make this bigger for all of us. So just a simple print statement, the mean of the house prices. And I'm going to go ahead and round this. And then I'm going to also pack this into an F string. And so I'll just do that, mean. How about that? Okay. And then let's do the median. And that looks good. And then we'll kind of discuss what we see here. Okay, so mean of 620, median of 582. 582.5 I think is fine as well. I guess I'm taking 3 significant digits here and just making it 582. There's nothing wrong with 582.5, and I think that might be a nicer way to represent the median as well. So thinking about these two values in relation to the data, you know what? Let's go ahead and put a sorted version of this. So let's print the sorted house prices. And we'll grab that as well. Offhand, you might be noticing we've got this high value of 1285. And this might, bring up the question, well, is 1285 representative? And you might notice also that we've got this low value of 350, and we might ask the same question there. My argument would be to go with the mean on this, but that we don't have enough information to really decide between the two. That's what I'm thinking. Now, my reasoning for this is that, well, what if we look back at other months, and every once in a while we do have, or we have enough home sales that are, $1.2 million homes or $1.3 million homes. I think we might start seeing this this high value that may offhand seem like an outlier because it's a sample, as actually being representative of values that occur in the data set. Now, if we were to see that, okay, well, this $1.3 million home, where's this Alameda? Okay, so really I think all the homes are going to be, way higher than what we're looking at here. But, if what we're seeing is that that's not something that occurs too often, well, we'll probably think median is a better measurement of center here. So I think we need more context, but I think you can make a fair argument for either median or mean in this case. I think most people would make the argument for median, but I'm on team mean for this one, just because of assuming that we are going to have these higher values that come up. Okay. So I'm going to comment that out. And let's think about another measure of center. And this may not seem like an obvious measure of center, but let's talk about it. So the mode. We can think of mode as just being the most occurring item. And we're going to do a simple mode here, just a single mode. What is the most occurring item? But let's say we've got, I don't know, I was about to say we have an animal shelter, but then I started, feeling sad about how we're going to think about the distribution of animals. Let's say we have a collection of things that people are interested in. How about that? And how would we quantify the median or the mean of that? Oh, well, this person's into biking, this person's into juggling, this person's into skydiving. I don't know. Like, how do we say, well, the mean thing is some smash together of juggling and cycling while skydiving? That probably not. That's not how we would really think about that. We can't apply mean and median to anything that's not numeric. And so we have this idea of categorical data, right? Something that is descriptive of data. Descriptive of a phenomenon without being numerically descriptive necessarily. So there's a statement in here: the mode is not very useful for continuous data. There's truth to that, and we'll talk about that more probably when we get to distributions. So this idea that we're, rather than seeking the center of the data set, we're just seeking the item that has the greatest frequency, the most highly occurring item. And even though we're not going to get into it, we can have a most occurring, a second most occurring, a third most occurring, and so on in a data set. And give me 1 second. My cat is meowing at the door, and I want to let him out of the room. Apologies in advance for, all the appearances of my cat. He's going to be around. Okay, so there's this idea that we don't really think about mode in terms of continuous data, and I'm going to make just a quick argument to contradict that. Except it's not really about mode; it's about bins. Okay, now what do I mean by bins? Let's say we have some data set, and instead of using A, I'll use B, right? And we've got 0.013, we've got 9.72142, right, and so on. And the highest value we might see is 100, right? So let's imagine there's a value that's like 98.221. So we've got all these values in between, I don't know, hundreds of values, let's say. The way that we might think of something like mode for continuous data is, well, let's make bins. And let's say, well, 0 to 10. And then, essentially, of course, 10 is going to be either inclusive or exclusive here. So this maybe will just be slightly greater than 10 to 20, right? And so on. And finally, the highest bin is going to be 90 to 100. So, we might count the number of items that fall into each of these bins. We obviously have an item that falls in here. We have an item that falls in here. We actually have 2 items that fall in here. And let's imagine, we just have, I don't know how I want to represent that, but we've got some distribution that at the end of the day maybe looks like, didn't actually mean to draw that like a normal distribution, but we kind of section this out, right, into 10 bins. I'm not sure if that's 10, but 1, 2, 3, it doesn't matter. The most frequently occurring items are going to obviously be where the count is the highest. And that we can think of as something like the modal bin. So, we might say something like, well, mode doesn't apply to continuous data. Continuous in this case just meaning that we've got decimal points, although we'll talk about that a little bit more. We can still think of mode in relation to that, right? What we might expect as representative. But more often, we're thinking about something like this, where, we've got, art and I don't know, baseball, right? And we've got all these categorical things that we can't really add up art and baseball and divide by 2. Okay, so how do we think about coding something like this? Well, I'm going to leave that to you. There's a number of different ways you can do this. That's why there's very little in the way of explanation here. Mode is going to take a list, and you're going to return the most frequent item in that list. So I'll go ahead and put 5 minutes on the timer. And yeah, see where you get with this. Okay, so let's look at this. I think this is kind of one of those. How do I say this? There are functions that I think of as being kind of good archetypes for things that you're going to do a lot, and I think the mode function is like that. I think the median function is like that. Let's think of a good way, or just a way to code this. This isn't the only way, but this is a way that will work. So the first thing I'm going to do is I'm going to make a list of items, and maybe I'll stick with that list of interests thing that I was talking about. So juggling, skydiving, how about baseball, and fencing, and maybe fencing again, and maybe skydiving again, and maybe all of these again. Right, I'm just sort of randomly building a data set here. And maybe juggling a couple more times. And, looking at this, what is the obvious mode? Well, I think the mode should be juggling here. So let's go ahead and define the mode function. So def mode, make that a bit bigger. And a way that I'm going to show how to do this. Again, this isn't the only way. I'm going to do this in kind of the most brute force way. I'm going to say that there's, some modal value, and I'm going to assume from the beginning, I'm just going to assume that maybe it's the first value in that list that I pass in. So from then on, so I can check every other value against that. And if the occurrence of any other value, any other item, it happens more in the list than the current modal value, then I update the modal value. So for each item in this list, and notice that I don't actually need to look at the first item, although logically this will be the same thing. But I'll go ahead and tune out the first item because I think this comes up a lot. This construct comes up a lot. So if list.count of the item is greater than list.count of that modal value, then we can update the modal value. So this is going to get the item. So that's pretty straightforward. We're just looking across the whole thing and making a decision. Okay. And then we can return the most occurring, the modal value. Okay. All right, so we've got this mode list, and we're expecting juggling. So let's see if that's what we get. Do mode on, what is that called? Mode list. Okay. Is that? Yeah. All right. Not supported between string and int. Well, that makes sense because list.count of item, there we go, is greater than list.count of the modal value. I think that's what was wrong. Yeah, and juggling. Sure enough, we get juggling. Now, in this logic, notice that we're not accounting for two modes, right? So that's something to consider. How would you account for two modes? Or how would you build this list in such a way that you would get the first, second, and third mode, right? How would you rearrange, how do I say this? How would you return a list with the primary mode, or, if it's bimodal, then the first two items have the same count? How could you return that, in the order of most frequent item? That's another algorithm to think about in regards to mode. So let me paste this in. and then we can talk about something a little bit different. So there's a question here. Why can't we just use max? Max is going to look at... so let me print the max here. The max of the mode list. What will that be? That'll actually be skydiving. If we think about the max in terms of in terms of these items, the first way to consider this is in terms of the order of ASCII characters, the order of actual characters. Luckily, everything here is lowercase. So which has a greater value, S or J? You know, which has a higher number representation? Well, it turns out that S does, actually. And so, you know, if I was to put, well, let's do zebra watching, right? Then what we're going to see is that zebra watching is the max value in there. So hopefully that clears up what's going on there. We actually are worried about the counts of things and not the actual comparison by numeric value. Letters, you don't need to jump down this rabbit hole or anything, but letters have a numeric value for us. But we don't really use that quality of letters in Python. You might use that in other languages a little bit more, but not so much in Python. Oh, sorry. Let me look at that. Multiple counts the same, so it defaults to the value we set. Oh, here, why don't we... Let me just make sure there isn't a logical error in here. I'm going to put swimming in here at the beginning. Hopefully we don't get swimming, and if we do, I'll fix it. Oh, of course we don't get anything because I commented out the code. No, we still get juggling. So max set list key gets list count. Yeah, we can think about that. Yeah. So let's look at that after class really quick. So we'll look at that environment setup a little bit, or the person who's having trouble running code, and then we'll look at your at sort of picking apart max of set list comma key gets list count. But yeah, I'm happy to talk about that, but we'll put it outside of class, or at the end of class, that is. Okay, so let's kind of shift gears, and we'll maybe wrap up here, but wrap up with this concept. So we're going to think about continuous data versus discrete data. This is going to come up a lot. I'm going to kind of repeat this a few times. So if you don't get it now, that's fine. Not that it's a very complex concept. I'm going to explain this how I think about it. And there are multiple ways we could think about this. Okay, so we're going to think about continuous versus discrete. So how do we think about continuous data? The way that I think about this is in terms of measurement, okay? So let's say, I think time is a nice continuous value. As far as we know, time is deemed to be continuous. Maybe it is discrete, but that's a whole other discussion. Let's say this is 0 seconds in the future, and this is somewhere over here, we're around 60 seconds in the future. Now, how are we measuring this? If we have a counter that has the precision of 1 second, then, then, right, there's going to be 60 of these hashes. The most that we can assume, the closest measurement we can get is, 1 or 2 or 3 or 4. But what if we have tenths of a second? Well, then we get these values in between, right? A lot more values than that, but we get to look closer and closer. And if we, kind of... Great. Okay, wait. There we go. That's what I was actually trying to do. If we zoom in on some moment, and that moment is a segment of time, well, we can do that again. We can zoom in on this moment, and we get a segment of time. And we can do that again and again and again. And if we have a precise enough tool for measurement, right, like the most precise clock in the universe, let's say it's infinitely precise, then we can get an infinitely precise measurement, right? Of course, theoretically, that's a little problematic, right? But that said, our idea of continuous is sort of rooted in this idea of infinite precision. The further we look into something, we can just keep doing that forever. So continuous data kind of has that property, right? We can think about time that way. We can think about people's heights that way, right? If we have a precise enough tool for measuring people's heights, then no two people on Earth are going to be the same height. Depending on how high their hair is sticking up that day or something, right? Like this is contingent on our tool for measurement. So discrete is going to be different from that in the sense that discrete is not so much about measurement, it's about counting. And, an easy way to think about this is that, well, the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., are discrete values. And if we think about this on just a number line, well, okay, so let's go from 0 to 10, and, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The way that we might think about this is that there is nothing in between 0 and 1. And there's nothing between 1 and 2. This is the value, maybe we can say this is the value 0, and this is the value 1, and all of this is the value 2. We can't have a 1.5. We can't have a 1.5932 whatever. Discrete means that we have some discretized unit, right? We have some arbitrary bounds that don't allow us to go in between. So we can take that a little bit further, because I don't want to say that discrete is, whole numbers, right? Discrete data, we can think of, well, let's think about the space between 0 and 1. And, we have, 0.1 and 0.2 and 0.3 and all the way up to, 0.9 and 1.0. This can be discrete, but again, we want to think about this as there not being anything in between 0 and 0.1, right? We don't have a 0.05 in this system. So discrete just means that we've got these discretized chunks. Fundamentally, a computer stores things in a discrete way, and it stores those things in binary. And we're going to get into binary a little bit more than probably a lot of people are comfortable, but we're going to get into binary. And we're going to see that we never actually have discrete values in a computer. Even when we have really long decimal places, all of that is being stored in a discrete way, as it turns out. So in some way, in a computer, we're always dealing with pseudo-continuous data because the method of storing numbers is actually discrete. But that's, we won't dive too deep into that, but I'll probably reiterate that point a few times. And let's see if we've got enough time for this last little bit. No, you know what? I think I'll save this for next time. I'm going to state this now and talk about it a little bit. And, I've already said this to some degree, but we're going to put this into a practice that, throughout this course, I'm going to be bringing this practice up. Okay. So, how we think about sampling? Well, as I said before, we're sampling from a population, and we want to make that sample representative. And we're trying to, in many cases, we're trying to approach what we think of as some universal truth, that population parameter that's out there in the universe. That's not the only perspective on this, right? Some people are like, well, that's an unknowable thing, so why do we worry about it? And we take maybe different approaches. But let's think about it for now as we want our X bar to approach mu. We want it to be as much like mu as possible. So we might make an assumption that there is a mu to be found if only we could get all the data in the universe. Well, that's a problem. We can't get all the data in the universe. And I'll just say this one more time. When we're talking about a population, the way we refer to the moments or the metrics in that population, we refer to those as parameters. Not to be confused with parameters to functions, but same word. So when we talk about mu, we are thinking about that in terms of being the truth, if only we could know it. And when we talk about measurements on samples, we talk about them as statistics, right? And that's X bar for us. And we want X bar to be as much like mu as possible, that theoretical mu. So let's call it there. I'm going to go ahead and stop recording. And